Recently, I asked myself a question: are we capable of visualizing 4 spatial dimensions? We easily visualize the universe with 3 spatial dimensions: length, width, and height. But can we mentally manage to visualize a 4th spatial dimension? What would it actually look like? Is it humanly possible? Does physics itself allow this idea of an additional dimension? When I asked myself this question, I was far from imagining that all of this was actually just the tip of the iceberg in the complex and submerged structure of physics. Well, we can already guess that trying to visualize a 4th spatial dimension when our universe only has 3 spatial dimensions, it is quite complicated. And for now, I'm not going to venture into the territory of the 4th dimension of time yet. We're going to try to stay within a mathematical framework that is extremely understandable. And to try to get even a vague visual understanding of what a 4th dimension will be for us, observers of 3-dimensional reality, it can be quite useful to try to put ourselves in the place of observers in a 2-dimensional reality and to try to understand what it will be like if a 3-dimensional outsider collided with our reality. I just want to clarify, because I haven't yet taken the time to define what a dimension is, that in the classical geometric sense, a dimension is simply a direction in which one can measure the position of a point or an object. The 3 spatial dimensions are obviously length, width, and height. Normally, they are familiar to everyone. Every object we observe around us exists in these 3 dimensions. And the position of any object can be determined by 3 coordinates. That said, that doesn't prevent us from knowing objects in 1 or 2 dimensions, of course. Since primary school or even kindergarten, we are used to dealing with 2-dimensional objects, polygons. If we go one step further and add a dimension, we get polyhedra. And if we go even further, then we are no longer dealing with 3-dimensional objects, but with n-dimensional ones, so as many dimensions as we want, and we enter the domain of the most general term possible, polytopes. Now that we know this, we can move into the world of polygons. This 2-dimensional world, which is just a plan, is not a new idea, but comes from Flatland by Edwin Abbott. When I did my research and came across this book, I felt like the name wasn't unfamiliar.
Flatland.
And after looking into a bit more, I realized why it felt familiar. Sheldon Cooper in the series The Big Bang Theory talks about this word.
I am now a hexagon in 2-dimensional space and can only perceive the edges of other objects.
As he says so well, he sees himself as a hexagon in that world. And that makes sense because in a planar world, only polygons can exist, of course. And technically every 1-dimensional object. So, Flatland is a critique of society, where shapes represent social classes. This book develops this universe in which a polyhedron, that is to say a 3-dimensional object, like a cube, enters the reality of polygons. For the inhabitants, for the polygons, the presence of a cube would be extremely shocking. It would suddenly appear, then disappear a few moments later. If we tilt it just a little bit, the polygons will first see a triangle, then a hexagon, and finally a triangle again before seeing it disappear once more. Thus, you and me, as beings living in a 3-dimensional reality, we could say that such an appearance of a 4-dimensional object in our reality would have an equally shocking effect. But one that we could, in some way, understand. We could understand that our perception of this object is limited by the dimensions we are capable of visualizing. The simple question that is therefore legitimate to ask is the following. How, being only in a 2-dimensional world, could one try to visualize what a 3-dimensional object actually looks like? For that, there are different techniques. We see that the inhabitants of Flatland could visualize 3-dimensional objects using several methods, like slices, which correspond to the example I gave just before. Then there is unfoldings, where we see the net of the object. And finally, there is projections. Well, visualize is not really the right term for the situation. It will be more accurate to say represent. Because in the same way as the inhabitants of Flatland, we cannot truly visualize a four-dimensional object. But we can form certain representation of it using methods such as nets. The net of a cube could help the inhabitants of Flatland represent the cube. That's the method of unfoldings. And we, in the same way, could have the net of a hypercube, which would be a four-dimensional cube. And that would help us represent what such a hypercube would look like. Thus, the story of polytopes, and even the story of Alicia Boo, the one that discovered polytopes, is extremely interesting. By the way, there is also a Flatland film on YouTube. I haven't taken the time to watch it yet, but it could be interesting, I don't know. But anyway, what I'm trying to do here is not to understand all the dimensions that can exist mathematically, because we know that we cannot visualize them. We would end up in a mathematical territory that is far too abstract, and I think it's better to stop here with things that are still quite visual, which is already pretty good when you're starting. No, here the goal is to focus on the very existence of a fourth dimension, or even more, in reality. Mathematics predicts the existence of everything that has a logical structure in abstraction, where the only real problem is nothingness. The realm of mathematics is a wonderful land where infinity roams freely. But in the world of physics, which is the real world, infinity is something we strongly dislike. So the question is extremely simple: does current physics allow additional dimensions? And that is where the most fascinating and well-known modern theories, at least by name, provide us with some answers. The theories I'm going to talk about were not developed by chance. Their very existence is due to the shortcomings of modern physics. And the symbol of physics at the macroscopic scale, that is the scale of large objects, is the theory that reigns supreme, and that is the Albert Einstein theory, general relativity. With this theory, saying that there are only three dimensions is incorrect. Or at least, when I say that, I'm not being precise enough. The theory of general relativity adds a fourth dimension, time. It describes a universe where there are three spatial dimensions and a fourth dimension, which is time. Three spatial dimensions for one temporal dimension, that is what we call space-time. In general relativity, space-time is a unified entity. The universe is not just a space in which events occur, but a dynamic structure that can curve under the effect of gravity. This implies that massive objects, such as planets or stars, curve space-time around them, creating what we call gravity. Here I'm showing you a three-dimensional model of space-time, which is not mine, of course. But generally we're used to representing space-time with only two spatial dimensions, like a sheet on which the objects of the universe are placed. However, you must keep in mind that there are indeed three spatial dimensions in general relativity. As I said, general relativity unfortunately does not solve all the mysteries of the universe. In particular, when it comes to reconciling its strong point, gravity, with the other fundamental forces of nature at macroscopic scales, when we enter the domain of quantum mechanics. When we try to explain observed phenomena such as dark matter or cosmic inflation, the limitations of general relativity and classical physics become quite significant. And it is precisely at this point that modern theories, such as string theory or loop quantum gravity, which propose the existence of additional dimensions, come into play in an attempt to fill these gaps. So, string theory is one of the most ambitious, and moreover, one of the most fascinating, attempts to unify the fundamental forces of nature within a coherent theoretical framework. It was initially developed in the 1970s to explain certain anomalies in the interactions of elementary particles. String theory proposes that the ultimate consistence of the universe are not point-like particles, but one-dimensional objects called strings. These strings vibrate at different frequencies, and their modes of vibration determine the properties of the particles we observe, such as their mass and charge. One of the most intriguing aspects of string theory, and the one that interests us in this video, is that it requires the existence of additional dimensions to be mathematically consistent. In fact, it is important to know that there are different versions of string theory. For example, in the most well-known version, superstring theory, for the equations of the theory to work properly, the universe must have not 4, but 10 dimensions, 9 spatial dimensions, and 1 temporal dimension. Of course, this number of dimensions may seem counterintuitive, if not outright absurd to us observers in 3 dimensions, but these 10 dimensions arise directly from the complex calculations underlying the theory. So, where are these additional dimensions hidden? According to string theory, these dimensions could be compactified, meaning they are clubbed up on themselves at such a small scale that they are undetectable with current scientific instruments. To understand this, there is an example I like. I take a sheet of paper. We can clearly see that at large scale, because if we zoom in, we see it has thickness. This sheet appears to have 2 dimensions. But if I roll it into a very thin tube, to the point where if I keep going again and again, well, here it's not possible, but if I keep going, we can no longer see the whole. And then it could look like a string or a thread. Basically, it could appear one-dimensional to someone who cannot perceive the curvature, meaning someone very far away. In exactly the same way, the extra dimensions could be curled up in such a way that scientists cannot detect them directly. These additional dimensions could have complex geometrical properties. Theoretical physicists have explored mathematical shapes called Calabi-Yau manifolds to model precisely these dimensions that are invisible to us. Each Calabi-Yau manifold has a specific structure that could correspond to different types of particles and forces that we observe in our universe. The specific shape and configuration of these extra dimensions will determine the characteristics of elementary particles and fundamental interactions. So here we need to pause for a few seconds, because the implications of the existence of these additional dimensions are crazy. Just to give you one example, they could provide an explanation for the relative weakness of the gravitational force compared to the other fundamental forces. For those who don't know, in our universe there are 4 fundamental interactions, and gravity is the weakest of them. If we assume that part of gravity leaks into these extra dimensions, then that could explain why gravity seems so weak at our scale. That's pretty wild. And here I've only talked about superstring theory. If we want to go further, we can also talk about another variant, which is M theory, which proposes yet another additional dimension, bringing the total to 11 dimensions. But I'm not going to dwell on the theory for now. Honestly, just like a superstring theory, it deserves a video of its own. For now, there isn't one on the channel, of course, so if you want a clear explanation with incredible animations, as usual, I let you go check out the video from the colleague Science Click. Alright, before moving on the theory that will probably interest you more, since we are going to talk about the multiverse, there is another major theory beforehand that introduces additional dimensions: loop quantum gravity. So, the theory is another major theoretical approach aimed at unifying gravity with quantum mechanics. Unlike approaches such as string theory or M theory, which directly add extra dimensions to solve certain problems in physics, loop's quantum gravity adopts a much more radical idea. It questions the very nature of space and time themselves. To understand this, we first need to clarify an essential concept. In classical physics, as in general relativity, space-time is considered continuous, meaning it can be divided indefinitely like a line with no grain. In contrast, something discrete is made of indivisible chunks, like pixels on the screen or bricks forming a wall. Loop quantum gravity proposes precisely that spacetime is not continuous, but discrete. It will be composed of tiny fundamental units called quanta. A quantum is simply the smallest possible quantity of a given physical property. This term, of course, is also used in quantum mechanics, where energy is exchanged in packets called quanta. Here, the idea is similar but applied to space itself. So there will exist grains of space-time impossible to divide further. That's clearly incredible. In this theory, these quanta are not little rigid cubes, but rather abstract elements connected together in the form of loops. These loops intertwine to form a kind of web called a spine network. This web or network constitutes the fundamental fabric of space. What we perceive as a smooth and continuous space at large scales would actually be a structure made of these microscopic links, like a fabric whose threads we cannot see from afar. And so, because we have to get back to the topic of the video, of course, regarding extra dimensions, the difference with string theory is that in the latter, the additional dimensions are assumed from the start as necessary for the mathematical consistency of the model. In contrast, in loop quantum gravity, the existence of extra dimensions is not assumed from the beginning. Instead, it is considered that they could emerge. Thus, extra dimensions will not be dimensions already present in the universe, but could appear as a collective effect of the structure of the loop network. At extremely small scales, the discrete structure of spacetimes becomes dominant. At that level, it is possible that new directions or degrees of freedom appear within the network, giving the impression of additional dimensions. In summary, loop quantum gravity proposes a vision in which spacetime is made of elementary building blocks connected in a network. The dimensions we know, our reality, might only be a microscopic approximation at large scales of this deeper structure. And any additional dimensions would not be fundamental, but rather an emergent result of this quantum architecture. Alright, I admit that when I first got interested in science years ago, I was convinced that the multiverse was just a sci-fi concept. And by learning more about quantum mechanics, I realized that I thought shit. In fact, the idea of parallel universe has a serious theoretical foundation in quantum mechanics through many worlds interpretation. And yes, it's a real theory that was first proposed by Hugh Everett in the 1950s. This theory is, we have to admit, a radical interpretation of quantum mechanics, where every quantum event leads to branching of the universe into as many branches as there are possible outcomes. Thus, rather than a single universe, the many worlds theory suggests the existence of a multiverse composed of an infinite number of parallel realities. To understand the many worlds theory, it is essential to go back to one of the most puzzling aspects of quantum mechanics, the measurement problem. According to quantum mechanics, particles such as electrons can exist in a state of superposition where they simultaneously occupy multiple possible states, each associated with probabilities. It is only when a measurement is made that the superposition collapses into a single observable state. The question of what causes this collapse has led to many interpretations, among which the many-world theory stands out for its boldness. In Everett's interpretation, the collapse of the wave function is not a real physical event. Instead, every possible outcome of a quantum measurement is realized, but in a separate universe. For example, if an electron can be measured with a spin up or down, I made a video about the spin, the universe splits into two. In one, the electron is observed with a spin up, and in the other, with spin down. That's huge. This branching happens for every quantum interaction, inevitably leading to the continuous creation of parallel universes. That will be insane. And once again, to come back to the topic of the video, the idea of extra dimensions could be integrated into the framework of the many-world theory in several ways, actually. On one hand, these dimensions could represent hidden or unobserved aspects of other parallel universes. Each universe could have its own configuration of extra dimensions, invisible from our reality but fully manifest in other. On the other hand, and this is just as interesting, extra dimensions could provide the necessary space for these multiple universes to coexist without interference. Parallel universes will not be separated by conventional spatial distances, but could be stacked within additional dimensions. This will mean that although we only have access to our own universe, others could exist in immediate proximity within these hidden dimensions, separated from us not by space, but by another dimension. This theory is phenomenal. It would be amazing to explain parts of Rick and Morty using this theory. Alright, if we want to look at the implications, it's quite easy, but also disturbing. From a philosophical point of view, this theory clearly challenges the idea of a single objective reality. If all possible outcomes of a quantum event occur in parallel universe, this raises questions about the nature of reality and consciousness. Every choice we make could lead to branching of the universe, with a different us existing in each branch. But from a scientific perspective, the many-world theory could offer a solution to certain paradoxes in quantum mechanics, such as Schrödinger's cat. In this paradox, a cat is both alive and dead in a superposition of states until an observation is made. Well, in the many-world framework, the cat is alive in our universe and dead in other, thus avoiding the need for a mysterious collapse of the wave function. Alright, we still need to come back down to Earth a bit. Because, as you can imagine, the many-worlds theory is difficult to test experimentally, since parallel universes are, by definition, inaccessible to our direct observation. Some physicists consider the theory an elegant mathematical solution, but not really a literal description of reality. But honestly, all I take from this is that Earth 616 could exist somewhere in the infinity of the multiverse. I hope you enjoyed this video. Let me know what you thought. Do not hesitate to like, post, comment, subscribe, and even share if you're crazy enough. And all that is left for me to say is keep dreaming, keep learning, stay curious. See you next time.